recording this lecture for continuation of Verilog language. And today our focus will be on these constructs that are the initial block, the always block, okay, and we will see what we can have the in terms of coding. Just we'll look at constructs like if statement and loops, as I stated earlier in a previous lecture, that Verilog resembles C and C plus in these constructs, the if statements. In many of the data types, the while loops, the for loops, okay, and that's why it is easy language to learn because of these similarities. Of course, it has its own special things like the wire, the register, and they make the language more appropriate for hardware. We have that subset which is different from C plus, but again, we have the other part of the language which looks exactly the same as C. And today we'll look at these constructs and structures that can be coded in the initial and the always blocks, and we will see that they are similar. The task and function, we'll look at it in the second in the following lecture. Okay, so initial blocks and always blocks, they are the main blocks that are can be seen in Verilog code, and what they mean is the following. The initial block here is executed once. Okay, so you start this initial this initial block, and excuse me, and the always block. So the initial block is executed once. However, the always block is an infinite loop. It execute it execute the block, and then once it finish execution, it goes back and executes it again, etc., etc. Of course, to prevent your simulation to hang and you have an kind of infinite loop in the sense of infinite loop in the case of C and C+, we have some guards here that prevents this from happening. We wait for events, and we will see how we code that. But the point is, once you execute the block once, you go back and execute it again, and then you execute it. Once you are done, you go back and execute it. So the main difference between initial and always, initial block, the statements between begin and end are executed only once. Done. But the always is repeated until the simulation is stopped. Okay. Now, here are the syntax issues. So we have initial, begin, end, and you have statements, right? And if you have just a single statement, you don't need begin and end as here. And for the always block, we have this at here. And this at is, it's kind of wait until something changes here in the sensitivity list. We call the sensitivity list, are these the set of signals that are being used inside the always block. So if this one of the signals has changed, then we go and we execute the block, and then we come back and wait here. We wait for another change for one of the signals. If one of the signals have changed, we get inside, we execute and come back, etc., etc. So between the begin and end, you have certain statements that are executed, and we will see if you can specify certain signals to be observed if they change, or you can say whatever changes, execute the block. And this is the syntax. At with the two brackets and asterisk says that whenever anything changes, anything means what? Inputs to the always block, then execute the block. Okay. So now, one of the statements, now anything with a dollar sign here, by the way, it is direct. These are directives to the compiler and the simulator, meaning they do not implement hardware. So dollar sign monitor, it monitors certain signals and prints their values. Dollar sign display, it prints the values of signals. What is the difference between the two? Monitor, always monitor a change on a list of signals. Display, it prints the values of the signals just once. Okay. Another simulation directive here is finish. Whenever this is encountered, we finish the simulation, or we can suspend it, which is stop. So finish, it quits the simulator. When the simulation, it quits the simulation, sorry. Stops, it just halts the simulation. So you can re-kick the simulation if you're using stop. These two statements, the finish and stop, commonly used in test benches when you want to either halt or finish the simulation. Okay. Now, so these are syntax of monitor and display, and you can much like we have in C and C plus language in terms of how you format the signals and the data type, etc. You can do the same thing. And now we have here an example of two initial blocks. Okay, so here is an initial block, and here is an initial block. At the start of the simulation, both of them, they will start executing. So in this initial block, what I'm doing, I'm changing the values of A. And in this initial block, the second one, what I'm doing, I am displaying the value. Now, what is this here? What is this here? What this means is that wait 10 simulation ticks, which is the unit of the simulator, and then do something. So here we wait for 10. So what we'll do here, let's plot the time the simulator starts. So here we start the simulator. Okay. So here between 0 time tick until 10, right? Until 10, which is right here. The value of A, so this is the value of A here, is unknown. We don't know the value of A. Then at simulation 10, time 10, the A gets the value of 30. So the A gets the value of 30. So this is the value of 30. All right. Okay. Then after 20 time ticks, okay, so we wait for 20 times 6. So this is 20. This is 30, a 30. Okay, a 30, which is here. All right. Then A becomes what? A becomes 40. Okay, so A becomes 40. All right. Now, um, so let's come here to this initial block, and let's use another color here, and we'll say this initial block, what it does, it displays the values of A. Okay, so this sets the value of A. This prints the value. This is the sort of the display of the value of A. So initially, when we start this executing this initial block, we'll come here at what time? 0, and we say display the value of A. So we'll look here, what's the value of A here? 0 is unknown. So that's why we print value of A is unknown. This is the output of the simulation. Unknown, it doesn't know. Now, after 10 simulation ticks, right, then we print the value of A. So what's the value of A? The value of A is right here. Now, it is interesting that here we will have a race condition. What do we mean by race condition? Either this will execute before the second initial block, and then we will set the value of 30, then we'll print it. It will get a value of 30, or we will execute this statement before this statement, right? And this then we'll get a value of an x here. So this is what we call two race condition. A race condition is a situation when in simulation you have two events. One of them can go before the other one. There is no determined way to. There is no deterministic way to tell the order of these two statements. So this is statement here, this is statement here, and this is statement here are in race condition. So one of them can be before the other one. That's why we don't know really what gets printed here. Okay? Right. Now, after 10 simulation ticks, right, which means at simulation 20, what do I print? Well, at simulation 20, I am here. I can tell you for sure that A equals 30. So this for me, A equals 30. Now, After 10 simulation ticks, which means we are right here, we also not sure if we can have the new value of A, which is 40, or the old value of 30. So again, this statement and this statement are in race condition. We cannot tell their order. That's why you have to be careful with these things. Don't create a race condition in your simulation, okay, especially with the initial blocks. But that shows once we are done with the initial block, all right, this one and this one, khalas, the simulation is done, complete, finito, because the initial blocks are executed once. And typically initial blocks are used for to initialize the hardware, to do the reset, okay, and to kick off various tasks in the system that need to be kicked once, okay. Another example here of display statement and setting of signals. So check out here, in this initial block, we set the value of A at 40. Oops, sorry. We set the value of A. Uh, see, take this one. We set the value of A. Oh, there is something here that makes it this funny character or funny shape. Okay, so we set the value of A here. Okay. We display it with different format: binary format, hex format, character, octal, and you can see this is the output, various all the format. And here in this initial block, what we do, we set the value of A and B, right? And then these are the examples, by the way, that you should do in your simulator. And very soon will allow you to download the simulator. I'm going to talk with the my assistant in the course to allow you start doing the simulation. So take these two simple examples and write them and compile them in your simulator. So this is A, B, and you can display their values. Okay, so you can see the format of A is binary, so that's what you have here, and the format of D is decimal. That's what you have here. You can also display with the print with the display statement things like the module name, the time, the library. Get fancy stuff, and you can get these are from different. You can get what you can print in terms of day and time and library from the manual of the Verilog. So dollar sign, I'm sorry, percentage sign M means module, percentage sign D means day, etc. So so you can print fancy stuff in the output of the Verilog. Here's an example here where we are really getting very sophisticated here. And so basically the idea here, you have two initial blocks, okay, all right, which changes the variable A, right? So this I'm sorry, this is initial block which changes the variable A, and this is an always block which changes the same variable A. Okay, here's my advice to you in Verilog: do not do this, meaning when you have multiple blocks like initial or always or multiple always block, don't have the same variable, which is in this case A, being modified or assigned to by different blocks. That's a very bad coding style, and it is almost certain that will create problem for you. Okay, so but in this example, what it's trying to display for you, what happens value of A. So we'll take it just in case of an example. So here you start the simulation from time 0, where A equals, so this is A, where A equals 0 here. Okay, and then after 35 you set A to X. So you go here all the way, and at time 35 here, 35, you set A to X. So here we set A to A0. Okay. And notice here at the other always block here, which it does after every 10 ticks, it inverts to A. So I will come here after 10 here. This is 10 here. All right. So A changes from 0 to A1. Okay, and then after 10, this is 20. A changes from 1 to a 0, and from 20 to 30, okay, A changes from 0 to a 1. Okay, so 0 to 1, okay, and to 0 to 1. And then in this block, we display the values of A at various times. So here in this block, which is this one, we will wait for 15, right? And then we display the value of D. So let's see if we choose this color. Let's say, for example, if we choose this here, so we'll wait till 15. So we are here. Okay, so what's the value of A? It is 1. So we display, right, the value of 1. And that's why you can see that this statement corresponds to this one here. Okay, and this 15 here is the time. Okay, so the time displays the time and the variable, which is in this case A. Okay, so at time 15, at time tick 15, the value of A equals 1. Now let's see what this initial block here does. It monitors the value whenever of A changes. Okay, so monitor basically it prints the value of A. So we will see that here. Let's pick a different color here. We'll see that here whenever A changes. Okay, so here A changes, and here A changes, and here A changes, and here A changes, and here A changes, right? Whenever A changes, we'll print the statement. So you can see that this is 1, 2, 3, 4, 5 times, and it will display the value of A. So here A, the value of A is 0. The value of A becomes a 1. Now this is when A sets back to 0. This is when A becomes an X. Okay, so this is the initial block. Now let's take a look at the always block here. And the always block, it says at this sensitivity list, meaning whenever A changes, then display the value of A. These are almost equivalent, these two statements, and that's why you will see those green ones. Okay, I see these green ones, those green ones. This one here, you will you will have A when it is set to 0 will print it. When it's set to 1 will print it. When it's set back to 0, we'll print it. When it's set to 1, we'll print it. When it's set to an X, to print it. It is, as I said, these two are equivalent. Okay, almost. Okay, but here is my problem with this example. We are setting A in two different blocks. Don't do it. Okay, not good. Except for the clock, when you initialize it, we'll see how this might be A-okay. Okay, another example of initial block, so do it yourself. Now here is one way in our digital system how we have an important signal, which is the clock, right? So how do we create the clock, right? So the clock goes something like this, um, this, this, and so on and so forth. Okay, so the way to create, there are multiple ways to do it. This is one way of doing it. And this is one place where I say we need initial block and an always block. And it's okay to set the clock into two different blocks, which is the initial and we will set it also in the always. So initially what we'll do, we'll set clock to equal to 0. Okay, so let's see. So this is here. So this is sets the clock for me at this time to 0. And then after 10 time ticks, yeah, right here. Okay, what we'll do, we will invert the clock. So the clock goes from 0 to a 1. Okay, then what? We wait another 10 time ticks. So we'll come here at 20. And then we'll invert the clock from 1 down to 0. And so on and so forth. And this is how. Okay, so what's the period here of this clock? Well, it is 20, right? It is 20. Okay, so this is how I create the clock signal inside my simulation. Typically, this is how you typically this resides in the test bench. Okay, so this is here how we show graphically what we have done. Okay, now uh, on always block, let's go back to always block and say this is what stops you here at the top before you enter the block. So what does that mean? This means that wait here until A changes or B changes or C, I changes. If any one of them change, then enter the block, the always block and execute it. In this case, what we do, we add A to B to CI to CI, and we set it to sum. Okay. Now, this is this will create combinational block with the same always block, and I can create a sequential block. And here is one way to implement the flip-flop. We'll see more examples of that. Always at the pause edge. When I use this pause edge, it means at the positive edge of the clock, right? Do this, which means update the output of the flop with the value of the input of the flop. Okay, so now here I created what? A D flip-flop. Okay, so this is combinational circuit. This is sequential circuit. Okay. Now we can now discuss how we can implement if statements, and if statements are very similar to what other languages do. So inside here, the always block, right? I can I can do an if statement, if A greater than B, do this. Of course, begin and end. These are the start and the end of my block. Okay, I can do nested if. So this is if else. Inside this if, I have if else. Okay, so nested if is allowed. Okay, and there is if else. Okay, so all that is allowed by the language. Okay, so you can see here if else if else. Okay, all right, so this is multi-way if statements like we have in other languages. Okay, I can have a case statement in Verilog which resembles the switch statement in C. So the case here where I could, for example, let's see if I have it. Then come back to here is, for example, implementing a multiplexer. All right. So in this case, this multiplexer, I have a multiplexer. The output here is out. Okay. And the input here I have here. I have what? I have A and B and C and D, right? And then I have a select line here. Okay, so now what I'm doing here in this always block, I'm implementing the multiplexer. So I do case select, check the value of the select. If the select is 0, then output is set to 1. 1, output B. 2, output C. 3, output D, and the default is X here. Default means none of the selection is correct. Okay, so this is how we implement the multiplexer. I can implement the multiplexer using an if statement, right? Which I don't recommend. So you can say F select equal this, then the out equals to this. And these two circuits are equivalent, but I prefer case. Case is a lot easier to implement if statements with. Now we can do the same selection on the assign statement. So wait a minute. Why the assign cannot use if statement? Assign, remember, from the syntax of the language, are those assignment that are outside the always block and initial. They are not allowed to use an if statement. Okay, they are not allowed to use. So what if I need to do an if statement? So we have a syntax special for them. Oh, I keep getting these things, funny characters. So here's what we will do. We can say the following. We can say assign equal, check the condition of the select. If it is equals to 1, if this condition is true, then the output is set to A. So out equals A. Now, colon else, this means else, check the value of select if it is equal to 1. If this condition is true, then out is set to B. Else, this colon means else. Check the value of select if it is equal to 2, then out is, if it is true, I set out to C. Else, check the condition of select. If it is true, out is set to the otherwise set the out to 1 over x. Now, this is how you use what it looks like an if statement on an assign statement. Personally, I do not recommend using this style of if statement with assign. I would rather, if I would to use an if statement, I'll use it inside an always block. Remember, you cannot use an if statement on an assign because an assign is outside always an initial block. Okay, so I do not prefer using this. I prefer you use an if statement inside an always block or a case statement like this. Very clean. Now, these at star means what? Whenever any of the input changes, what are the input to the block? The select, the A, the B, the C, the D. Don't tell me out is an input here. Out is the output of the always block. Okay. Okay. Now, the same multiplexer we are implementing it structurally. So we are implementing a 4-to-1 multiplexer structurally. Behavior using data flow style assignment statement and using procedural method, behavior procedural method using always block like that. And of course, for multiplexer, I prefer you do this type of implementation. I don't prefer. So this was an example here. Now let's go back to where so this is the case statement. We have repeat and while and for. And forever is an infinite loop. Forever do this. This is like an always. Um, Except that, yeah, you can have it inside an initial block. Repeat, it repeats this block. So repeat for, it will repeat this block 4 times. Okay, so it will repeat this block 4 times. Okay, kind of saves you typing. Okay, and while this is a while loop, okay, right, much like C exactly. Okay, and here a for statement for loop exactly like other languages. For A equals 0, A less than 8, so A will have value of 0, 1, 2, 3, 4, 5, 6, 7, because this is how we increment A, and every time we check this. Okay, all right, so this is very similar in syntax with other languages. That's why I'm not going to spend on it much time. Then we have these fork join statement, which we launch parallel statement. This is if you want to launch processes parallel in your simulation. So every one of these statements will be launched at the same time. Okay, so this is to launch concurrent processes. Okay, your simulations might not require that much of concurrency. So this is an example of shows you how concurrency. Okay, Those are concurrent statement, by the way, but we are delaying them purposely with these delays so that we can have these two blocks equivalent. These statements here are not concurrent. I'll wait for 50 and then I execute this. Then this statement, I will wait for 30 and then execute it, then reset. That's why you notice that the reset will be assigned. Oh, again made a mess. That's why you notice that this reset, right? This reset will be executed after what? After 80, 30 plus 50, 80. And that's why, because there is no waiting here, all of them are lunch in parallel. I have to make this wait till 80 because I want these two blocks to be the same. Just kind of illustrates to you that the fork and join statements are kicked off all at the same time. There is no, they are non-blocked. All are in parallel. Okay. All right. So what we have done in this lecture, we talked about the initial blocks and the always blocks, right? And what we can do inside them in terms of using the sensitivity list here for the always block, and that initial block is run one time, the always block is running constantly. We looked at what we can have in terms of if statements, for loops, and a case statement and other structures that I can implement in the always block. Okay, I'm going to stop the recording of this lecture and